All right, let's get right into it. We're looking at a huge 1 megawatt solar project in Kairouan, Tunisia. But we're going to focus on just one single number. It seems so simple, but it tells this amazing story about engineering, physics, and economics. And that number is the tilt angle of the solar panels.
So you look at the original project overview and it says it right there with all this confidence, 22 degrees. That's the precise angle to get the most sun all year round. Sounds pretty final, doesn't it? Like that's it, one perfect number for that one spot on Earth. But, that's where our whole investigation really kicks off.
Because that's the real puzzle, isn't it? Is getting the absolute maximum amount of sun the only thing we're trying to do here? As you're about to see, when you're engineering a massive utility-scale solar farm, things get way more complex. That one little number, it definitely doesn't tell the whole story.
So, to figure this all out, we've got to go back to basics, back to the first principles. Let's start with the textbook answer. What is the scientifically, theoretically perfect angle if all you want to do is capture the most possible sunlight over an entire year?
Okay, so here's the core idea. The simplest rule of thumb in all of solar engineering is this. To get the most energy over 365 days, just tilt your panels to match your latitude. It makes sense, right? This angle gives the panels the best average position to catch the sun, whether it's way up high in the summer sky or hanging low in the winter.
So, our project is in Kairouan, Tunisia, and that sits at a latitude of about 35.7 degrees north. So, if we're following that rule of thumb, the best possible angle should be, it should be right around 35.7, right?
Which means the scientifically ideal angle for year-round power in Kairouan is about 35 degrees. But wait a second, the project said 22 degrees. That's a 13-degree difference. In the world of solar engineering, that is a huge gap. So what on earth is going on here?
While the plot thickens when you realize that the word optimal can mean a few different things. What if your goal isn't just to get the most energy across the whole year? What if you need to generate as much power as possible during one specific season, maybe when everyone's blasting their air conditioners? Now check this out. If you want to squeeze every last drop of energy out of those long summer days, you'd actually flatten the panel's angle a bit, down to about 25 degrees. But if you needed to max out your power in the winter when the sun is low, you'd want a much steeper angle, something like 45 degrees. So see, 25 and 45 are also optimal angles just for totally different goals. And notice, neither of them is 35, and we're still nowhere near 22. And this brings us to the last piece of the puzzle. For a massive project like this one, it's often the most important factor of all: money. The real-world headaches of budgets and land use, they add a whole new layer to this problem. And this really is the million-dollar question, isn't it? Literally. Is your main goal to generate the absolute highest number of kilowatt hours? Or is it to generate the maximum return on your investment? Because for a giant solar farm, believe it or not, those two things are not always the same. And here's why. Think about it. The steeper you tilt your panels, the longer the shadow they cast behind them. That means you have to build your next row of panels farther away to keep them out of the shade. But what if you lower the tilt angle? Now the shadows are shorter. You can pack the rows much closer together, fitting way more panels onto the exact same piece of land. This boosts your ground coverage ratio, your GCR, and that can seriously improve the project's bottom line.
So what you get is this brilliant engineering compromise. Sure, you might lose a tiny fraction of energy per panel by tilting them lower than that perfect 35 degrees, but you can gain so much more overall by just fitting more panels into the same area. For a lot of these huge projects, the real sweet spot, the angle that perfectly balances energy production with the cost of land and construction, is somewhere between 28 and 32 degrees.
Okay, so let's put all these pieces together. We've talked about pure physics, we've talked about the seasons, and we've talked about economics. Now, finally, we can really understand how to think about what makes a perfect angle.
This table really lays it all out, nice and simple. There isn't just one right answer. There are at least 4, and each one is correct for a different goal. If you want pure, raw energy over a whole year, you go with 35 degrees. For that peak summer power, you choose 25. Need to prioritize winter? 45. And for a massive power plant where the return on investment is king, you're going to land somewhere between 28 and 32 degrees. So that original 22-degree angle, that just shows an even more aggressive push for economic efficiency. It's a choice that prioritizes land use and financial return above pretty much everything else.
So in the end, the answer to our little puzzle is that perfect is totally relative. The angle chosen for a solar project isn't just some number you pull from a physics textbook. It's a strategic business decision. It's the one number that is perfectly aligned with what that project is trying to achieve.
Which kind of leaves us with one last thing to think about. We've seen how physics, seasons, and economics are shaping today's designs. So, what's next? Will other things like maybe grid stability, or the cost of battery storage, or even changing weather patterns become the new driving goals that completely redefine the perfect solar design of the future? Makes you wonder, doesn't it?